Hello, my name is Renata Sabini, and I'll be sharing my NSERC US Array research project on transamination-based reactions of Zwitterionic quinones and gels, which I conducted in the summer of 2021, supervised by Dr. Louis Cuccia. I will begin this presentation by introducing the topic of crystal growth. There exists many techniques used to grow crystals, including growth from melt, growth from vapor, and growth from solution. Crystal growth from solution is of interest to my research, particularly crystallization in gels. Crystallization in gels is a very advantageous technique used to grow crystals. This setup is advantageous for optimal crystal growth and quality. The gel forms a network which essentially provides support to the growing crystal. There is no mechanical stress caused onto the surface of the growing crystal. Furthermore, nucleation is reduced, which leads to the formation of larger crystals. And most importantly, we can often see the formation of periodic patterns, which, as we will see later on, is very useful when it comes to the self-sorting of products. When it comes to the setup of crystallization in gels, the test tube is divided into two components, the inner electrolyte and the outer electrolyte. The inner electrolyte is what is confined in the gel. The outer electrolyte is dissolved in solvent. The outer electrolyte is usually of higher concentration than of the inner. This allows for the ions to diffuse from top to bottom. As the outer electrolyte diffuses from top to bottom, bands appear in a sequential fashion from top to bottom. These patterns are known as Lissagang patterns and are a result of chemical systems undergoing a precipitation reaction. These are examples of sparingly soluble salts crystallized in gels. Again, notice the Lissagang patterns. They result from irreversible precipitation. The bands are generated under non-equilibrium conditions. I am interested in seeing whether or not Lissagang pattern formation results from transamination, a reversible reaction at equilibrium. In 2002, Professor Olivier Siri and coworkers reported an interesting reversible transamination reaction of Zwitterionic quinones. Transamination can be defined as the transfer of an alkylamine from one molecule to another. Here we have the mass spectra for two different pure compounds. Each peak represents one molecule of a single molecular weight. The reason for which the molecule on the bottom weighs more than the molecule on the top is because it has two additional carbons in each alkyl chain. What was not shown in the previous slide was the mixed chain species. When an equal amount of two different amines are mixed, a statistical mixture of products is obtained. As previously mentioned, each peak represents one molecule of a certain molecular weight. The peak heights serve as a semi-quantitative measure of product distribution based on the observed 1 to 2 to 1 height ratio. We can see here that the Zwitterionic quinone with both the pentyl, the purple chain, and the hexyl, the green chain, is twice as abundant as either the dipentyl or dihexyl derivatives. Even though it is the same molecule, there are two ways of getting this molecular weight. The 3-component mixture can then be expanded to a 9-component mixture by using these 5 different amines. Based on the mass spectrometric heights, an almost statistical distribution of Zwitterionic quinones is obtained. The two lowest peaks in this statistical distribution are the 2,2 peak and the 6,6 peak. The height of all the intermediate peaks correspond to the different combinations of alkyl chains to get the same overall molecular weight. This is highlighted with the different colors in this figure. One way we can adjust the distribution of these products is by changing the solvent. The higher molecular weight product in purple is the least soluble, and by removing it via precipitation, the equilibrium will shift to make more of this compound. In chemistry, this is known as Le Chatelier's principle. To change the statistical distribution that was shown earlier, reaction solvents are modified in favor of the production of desired products based on differences in their solubility. Specially, the solvent is changed from acetonitrile/water to a more polar mixture of ethanol/water, in which the longer chain products are less soluble. The precipitate is enriched in the higher molecular weight products and depleted in the lower molecular weight products. As we can see in this work, the equilibrium is shifted simply by changing the solvent, which influences the solubility of the mixture's components. This is known as precipitation-induced self-sorting. Here is the setup for my research, where the inner electrolyte is one of the quinones and the outer electrolyte is one of the amines. The gel used is agarose gel. The positions of the precipitate, which, as previously mentioned, are influenced by their solubility in the gel, are investigated in my research. I am interested in determining whether or not the products of different solubility have different crystallization properties within the gel. Furthermore, I will be looking out for the formation of Lissagang patterns. So far, I have been performing many experiments in order to find the reaction conditions in which transamination of Zwitterionic quinones occurs in gels. Bands have been observed, like in this photo. I plan to continue these experiments and analyze the precipitate using mass spectrometry. I would also like to carry out the transamination reactions in silica gel rather than in agarose gel. I'd like to thank my supervisor, Dr. Louis Cuccia, as well as the members of the Cuccia lab and Dr. Yuan Fang. I would also like to thank NSERC, FRQNT, and Concordia for funding this project. Thank you.